Good day, class. In this last lecture of the unit, we're going to focus primarily on De Morgan's laws. De Morgan's laws are written here, and this is what they say. If you have A times B all inverted, it's the same as having the addition of A inverted with B inverted. And similarly, if you have A plus B all inverted, this is the same as having the product of A naught and B naught. And so you can think about this means in terms of the gates themselves. This we know is a NAND gate. So the output from a NAND gate is the same as the output here, where we have A going through an inverter and B going through an inverter and then into an OR gate. And this one, of course, is our NOR gate. So the output from a NOR gate is the same as having A going through an inverter, B going through an inverter, and then into an AND gate. Okay, so what we're gonna do in our problems today, first we're gonna write the Boolean expression corresponding to the original circuit drawing. Then we're going to simplify the expression fully using Boolean theorems and algebra. So the focus is on these two laws, but we'll also be using the 10 theorems. And then we're gonna draw the circuit corresponding to that simplified expression. Finally, we'll construct a truth table to prove the original and simplified expressions are equal. Okay, so in the lesson, we'll be reviewing a good portion of this whole unit. So let's get started. Here we go. This is our first example. So I've pre-drawn a circuit here, and we're gonna start. Part A is writing the expression that corresponds to the circuit. All right, so if you want, you can pause the video and try to write this expression yourself. But I'm going to do it now here as well. So you might find it helpful to start to write on the diagram. So we know that here we have A naught. This is B plus C, but then it's all inverted since that is a NOR gate, like that. And beyond that, the things are added, okay? Because once again, this is another NOR gate. So these two items are then added, and then finally that sum is also inverted. Okay, so we have A naught, and we also have B plus C all inverted like this. They are added together, and then that sum is also inverted. Okay, so this would then be the original expression for X. Okay, so we had an inverter and two NOR gates. Here's our expression. Now, part B. We're going to simplify the expression. When it comes to simplifying the expression, we begin with De Morgan's law, and we start by breaking this large bar here. When we break this large bar here, it changes this operation here. So take a look at the rule again. We're going to be using the second one here since we have addition currently. So what we do is we change addition to multiplication, and then the bar breaks right above that operation. So we'll have a smaller bar to the left and to the right of the new multiplication. So in this case, here's what we had originally. To the left and to the right of this operation. So the operation changes to multiplication, and that's where the bar breaks. So that large bar now becomes this. Okay, so again, this changed to multiplication and the bar broke here. So what do we have now? We have a double bar multiplied by b plus c double bar, just like that. Okay, now in simplifying the expression, since we've used De Morgan's law already, which rule do you think will be important? I think the focus should now be on Rule 9. In Rule 9, we see that a double bar is equal to a. So that allows us right here to change a double bar to a. This will stay multiplication. And this same rule, rule number 9, can be applied right here because we do have 2 bars of equal length above b plus c. So this just becomes b plus c. The only thing we have to be careful of, we still want to keep b plus c together because right now, given order of operations, this looks like a times b first, an AND gate, and then an OR gate plus C, because you would follow order of operations if you were to draw this. But B plus C has to stay together, so we actually need a bracket here. And once the bracket's there, this multiplication sign here is optional. So you can leave it there if you like it, or you can remove it. Maybe I can't remove it anyway, given my... there we go. My poor skills with this, what do you call these? Whiteout. Anyway, there we go. So that is all done for part B. And so now what would we do? Part C is redrawing the circuit, but this time drawing the simplified version here. So how would we draw this? Well, we would need an OR gate here. So now order of operations telling me that the brackets is drawn first. So one OR gate and then multiplication by A. So I'm gonna just draw that for you here. Okay, so as you know, I'm not great with the drawings, but we gotta have a round here for B plus C. So that's my B, that's my C, and that output is multiplied by A. So I might as well put A here. So that's my A. And then I want to multiply, so I need an AND gate. So I mean, I could draw a big one, or I could bend the wire a little like that. All right, and then I'm gonna draw an AND gate here. So straight in the front, basically, is what's required, like that. And that's it. And then at the end there, I'm gonna have my X. Okay, so what this algebra shows is that these circuits here would both perform the exact same function. The output of each would be the same. Okay, finally, part D. Part D, construct a truth table to prove the original expression is equal to the simplified expression. So we're trying to prove that this equals this. So maybe I'll write that for you, what it is we're actually trying to prove here. Okay, so, and also you could write it here. This would be the original circuit, this would be the simplified. Original expression, simplified expression. So we're trying to prove this is equal to this. So let's go ahead and construct a truth table. Now we have the letters A, B, and C. So we know this means we will need 8 rows in our truth table. So we use our pattern for A, our pattern for B, and our pattern for C. And now we're going to try to set up this left side. So remember that every time you would draw something in the circuit, that would indicate that a column is necessary. So A is going through an inverter, so I definitely need a column for A naught, and it would be 4 ones and 4 zeros. All right, so I do, of course, need B plus C all inverted in my truth table. But to do that, I'm going to first do a B plus C column and then follow it with a B plus C inverted column. Oops, like that. Okay, and this will be helpful also because it's in the right side expression. Okay. So let's do the addition first. So as long as we have at least 1 1, the output will be a 1. So we're going to have 0, 1, 1, 1, 0, 1, 1, 1. Which means that its inverse is 1, 0, 0, 0, 1, 0, 0, 0, like that. Okay, we still need 2 more columns for the left side. We need this addition, so the addition of A naught with B plus C all inverted. So let's put that in next. So here's the column for A naught. Here's the column for B plus C all inverted, and let's add those 2 numbers together. So 1, 1, 1, 1, 1, and then 3 zeros. Okay, to finish the left side, I need to place this large bar here. Of course, that corresponds to the little circle here, which changes an OR gate into a NOR gate. So this will be the last column we need for the left side. Okay, so it will be the inverse of this. So looks like 5 zeros and 3 ones. Okay, so that is the left side here done. It's the truth table corresponding to the original circuit. Now we're gonna need just 1 more column for the right side because we already have a column for B plus C. We just need to multiply that by the column for A. Okay, so let's go ahead and do that. So here is column A, right at the beginning, of course, and here's column B plus C. Now we're multiplying. So we need 2 ones to get a 1. So B plus C is here, A is here. So let's go ahead and check this out. 0, 0, 0, 0, 0, and now multiplying 1, 1, 1. And we're delighted because the column right here for the left side matches perfectly the column right here for the right side. So this means that our algebra in here was correct, and these 2 circuits do perform the same function. So to pretty this up a little, you know, you could do that and then also include all of these vertical lines. You know, you do have to draw truth tables on your test. I absolutely need you to be neat about it, okay? So that I can mark it. So please try to keep your numbers lined up so that I can read it okay. All right, so that's the first example done, and I'd like to go on to our next one. Here we go, example 2. So once again, I've pre-drawn the circuit. Let's go ahead. The first thing we're going to do here is write out the expression for x. Okay, and again, you can do this by marking up your diagram a little if you'd like. If you want to pause the video to try it on your own, go ahead. So here it looks like I have a NAND gate. So this is A multiplied by B and then inverted. Okay, so the multiplication again is implied there. What about this one? This looks like A inverted added, because it's round, to B. So here is A inverted added to B. So that is the wire here. This is the wire here. And now what's happening between the two things? They are multiplied and then inverted. Okay, so multiplied. Okay, so just a second here. So this guy for the top wire, this guy for the bottom wire. Now we said that they have to be multiplied together and then inverted. But, you know, again, the multiplication here would pull A naught this way. So when we have addition like this, we need a bracket around it. Okay, because this now means that there was an OR gate. So multiplication because of the straight front, and then the circle at the end, which turns AND into NAND, means a big bar like that over the top. So this is the perfect expression for x. Now, part B, of course, is go ahead and work on the simplification of that expression. And to begin with, we use De Morgan's law. So we have multiplication here. So we're going to use this top form. The multiplication becomes addition and the bar breaks right over that operation. Okay, so this turns into addition right here. Okay, so this is what I had to the left of the multiplication. And this is what I had to the right of the multiplication. So far, all I did was change that multiplication to addition. Now I have to worry about breaking the bar right here as well. Okay, so that means there will be this bar to the left of that multiplication and this bar to the right of where that multiplication was. So take a look again. Multiplication became addition and this bar broke here into that piece and that piece. Okay, lovely. And now let's continue using our theorems. So in the last example, I didn't actually make note of the fact that I used theorem number 9 to go from this step to this step, right? So I might want to note that. That was the A double bar equals A theorem. All right, so I'm going to use that one again right here. These two bars are of equal length, so this becomes AB. And I'll work on this one in the next step. So I'm going to write here that I'm using Rule 9 to change this term into plain old AB. And this one here I'm going to leave alone for the moment. But I will point out that when you do have this long bar over top of the sum, you don't strictly need that bracket any longer because the long bar serves as a bracketing feature anyway. Okay, so now in this next step, I am going to use De Morgan's law again. So we've got this big bar over top. We're gonna break it right over this sign here and it becomes multiplication. So the A naught that was there, the B that was there, we now have multiplication between and the bar breaks here. So it's now A double bar multiplied by B bar. Okay, so take a look at that again. We changed addition to multiplication. A naught got a new bar over it and B got a new bar over it. And that is the second form right here of De Morgan's law. So continuing now, inside this term, this becomes A times B naught. A double bar is A. So that looks pretty great. And you'd think we were done, but we're not. What can we do next? Well, look, A is common to both terms, so let's remove A as common. So dividing each term by A will leave us with B plus B naught, like that. And why is that so great? Which theorem becomes important now? This one, number 8. A plus A naught is 1. And so too is B plus B naught. So the bracket becomes 1. Now we have A times 1, which is A. And if you like, you can find that listed also in Rule 3. A times 1 is A. Okay, so we ended up using De Morgan's law twice. Once in the first step, and then we used it again right here for this expression, making it ultimately A times B naught. Okay, what did we find out? We found out that this intricate circuit really does nothing. The output is the same as the original A. So in part C, when we're asked to draw this, essentially you have A as the input, X as the output, no gates, nothing. I guess the circuit could look like that. So it's a pretty useless circuit, but I mean mathematically it was a good example. Okay, part D, a truth table to prove the original. So this is the original. We want a truth table proving that it is equal to this final simplified expression. So if you want, you can write that out. What you're trying to prove is this. Okay, so that's the original on the left side, and that's the simplified or final expression on the right side, and we're going to do this with the truth table. Now let's have a look though. We only have the letters A and B. What does that mean? Only 4 rows are required in our proof. Okay, so the pattern for A in this case looks like that. And the pattern for B looks like that. Now we have to set up many more columns to establish this left side. Notice that the right side is already here. So this is the right side answer. So we're hoping that when we're done setting up the left side, it will be 0, 0, 1, 1. Okay, let's work on that. So remember, the order of the columns doesn't matter. I think I'll do a column for AB, and then I'll do my AB naught. Okay, so anytime it's NAND or NOR, I need you to do 2 separate columns, okay? Once for the product and then once for the inverted product, or once for the sum, then once for the inverted sum. Okay, A times B, so multiplying 0, 0, 0, 1. A times B inverted then will be 1, 1, 1, 0. Okay, let's keep working on this expression. I'd like to do this one now, the OR gate, but first I need A inverted. So I'm going to do A inverted and then A inverted plus B. Okay, here's A. A inverted then, 1, 1, 0, 0. Now we're going to add A inverted with B. So when you add, the only time you get a 0 is if you are adding only zeros. So our output for A inverted plus B, we're looking at these two numbers, will be 1, 1, 0, 1. Okay, still working on the left side. I've got this column right here and this column right here. So I need to multiply those two columns together next. Okay, so I'm simply multiplying the two columns together. Which two columns? This one, which is right here, okay? And this one, which is right here. So we're multiplying the numbers. So we're gonna get 1, 1, 0, 0. There we go. It looks like we only need one more column, and that is taking this one and putting the big bar on top of it. Okay, so we have this column already, but now we need to invert it. This little symbol here is optional, okay? So here's the column, and now we simply invert it, making the output 0, 0, 1, 1. So that's the output for the original circuit. It's the output for the left-hand side here. We were trying to prove that it is the same as A. And you can see that we were successful. And so that means that our algebra in here is correct. We did a very good job. Sorry, I'm just trying to turn my camera angle slightly. Not having too much luck. Okay, in any case, we're very happy with that result. So let's give ourselves that happy face. Okay, I'm gonna do one more with you. I know the video is getting a little lengthy. It might be closer to 45 minutes, but I think it's worth it because as I said, here we're really reviewing much of this whole unit when we're doing these questions. Okay, here we go. Last one. So here's the original circuit. Let's go through our parts A, B, C, D. And we know that in the first part here, what we'd like to do is write out the expression for the circuit. So I'm going to just mark up the picture again just a little bit. So this is multiplication. This is multiplication. So what am I multiplying here? It looks like A is multiplied by B naught. Okay, and what about here? B naught is multiplied by C. And then what happens? Those are then added. See the smooth curved front? So they are added. So the two things are added, and then the whole sum is inverted. Okay, so let's write that out. We have A, B naught added to B naught C. Okay, so A, B naught is added to B naught C, and then the whole sum is inverted. Just like that. Okay, part B. Let's use our mad algebraic skills. So the first thing we're going to do is use De Morgan's law. So the big bar here is going to break, okay? So like this one, break the bar, change addition to multiplication. Okay, so this addition changes to multiplication. I'm going to write down what I had to the left and to the right of that operation first. Okay, so you can see here all I did so far was take the adding, change it to multiplying. The bar breaks right here now. So what does that mean? It means there's going to be a bar here and a bar here, like that. So the operation changed and the bar broke. Okay, so that was De Morgan's law. Now look, we are going to use it again here and here, De Morgan's law. Implied, of course, was multiplication in between. Right there, a missing dot, just an implied dot, and right here, just an implied dot. But that becomes very important now because those turn into addition. Okay, so we're gonna do this first one, and the multiplication right there becomes addition. And so I originally had an A to the left of the multiplication and a B naught to the right of the multiplication. So now those are left and right of addition. But the bar also breaks here. So now there's going to be a bar over A and a bar over B naught. Okay, so that's tiny. I'm sorry. You're probably going to have to zoom right in there. So the implied multiplication becomes addition. There is now a bar over A and a bar over B naught, resulting when this bar broke. This stays multiplication. Now we do the same thing here. The implied multiplication becomes addition. To the left of the multiplication, we had B naught. To the right of the multiplication, we had C. And now the bar breaks here, so we're going to have a bar over B naught and a bar over C. Okay, so this now says B double naught plus C naught. Okay, and over here, A naught plus B double naught. Now we have to be very careful because remember, we want to keep this together. Right now it looks like these two terms right here, using order of operations, are part of one single AND gate. And we don't want that. We still want to keep these together, okay? So that means put in a bracket. So when you have addition, you need that bracket to keep these binomials as required. Okay, and that makes sense with the picture, right? Think about the picture. Got to keep that together. Keep that together. Keep that together. All right, so in my next step, I am going to use rule 9, the one that says A double naught is A. So I'm going to use it both here and here to change B double naught to B. So this becomes A naught plus B multiplied, and this will be optional, that multiplication sign. This is B plus C naught. So this is what we have. Now, what did we use? Rule 9. Okay, now you have the multiplication of two binomials. I think you remember that this requires 4 terms once it's expanded. So we do first, outside, inside, last. So let's do that. The first term is A naught times B plus, on the outside, A naught times C naught. On the inside, B times B. And the last term, B times C naught. Okay, so that was doing first, outside, inside, last. Now, one of these terms really stands out to me, and it's this one. B times B is just equal to B, and that's rule 5. So let's use that here. Great, so we've got just a B there. And when you have a letter all on its own like this, it's really smart to common factor that, okay? Because it means you'll end up with a 1 inside your bracket if you do. So where can we common factor B? From this term, from this term, and from this term. We cannot common factor B from this term here. So let's put those 3 terms near each other so I can just change the order of the addition. So I'm going to write it like this. I'm going to put a B, then the A naught B, then the B C naught, and I'm going to leave the one term that doesn't contain B. I'm going to leave it at the end. Okay, so I just moved these 3 terms so that they were near each other. And then I will take B out of the 3 terms. And this last term will just be added at the end like this. Okay, so when B is removed from the 3 terms, the key is that you're using division, so there will be a 1 left here. B divided by B is 1. Plus, from this term, we'll have A naught, and from this term, C naught. So in the bracket, we have 1 plus A naught plus C naught. And why is that so important? Because at this point in time, which property becomes important? It's this one, number 4. Anything added to 1 is equal to 1. So 1 plus anything is 1. So this whole bracket becomes a 1. So again, the rule we used there was number 4. Now we have B times 1, which is B. B times 1, which is B, and that is also here. Rule 3 would say that B times 1 is B. Okay, and actually I forgot to make note of back here. We used a rule to change b times b into b. And that was rule 5. Okay, so I might write that down, that we used rule 5. I don't know if you want me to write it in this line or this line. I guess it doesn't really matter. But we did take b times b and change it into b. So that was rule 5. So this is a very long problem. You can see that we used De Morgan's law to start it off, right? From the original getting to this step. Then we used De Morgan's law 2 more times, once for the left and once for the right. Then we used property 9 for the double inversion. We multiplied the 2 binomials together. We then used rule 5 right there. Then we common factored b from the 3 terms containing b so that we could use rule 4, changing all of that to a 1. And here's where we are at, b plus a naught c. All right, sorry, b plus a naught c naught is where we're at. And this last step, if I were to try to draw this, I would need to draw an inverter on A, an inverter on C, and then an AND gate. And it might be considered even more simplified to draw this instead. One single NOR gate. So this would be using De Morgan's law sort of in reverse one last time to change A naught times C naught into A plus C all inverted. And I do that because it is a little easier to draw that picture. So when we draw our diagram, remember you don't have to have alphabetical order here. So I can put A closer to C and then add, so that was meant to be OR, and then circle at the end to change it to NOR. So I've got this part established, and all I have to do now is add it to B. So I'll do one more input here from B, and maybe even bend that wire up a bit so that it's closer to that one. So this is B. Okay, and so we need to show addition with B. So again, round in the front, and then it's just OR. Out X, like that. So that would be our simplified. So here's the original, and here would be the simplified. Final results. Okay, and lastly, I could do a truth table for part B for part D to show that the original is equal to the simplified. And I would need 8 rows because the letter C is involved. Do I have 8? 1, 2, 3, 4, 5, 6, 7, 8. I do. Okay, so I'm just going to start it here. I'm going to do an A and a B and a C using my patterns. And now I'm going to plan it out first before filling in all the zeros and the ones, okay? So I'd like to set up this original right here. So I'm going to do that by putting in a column for B naught. Then I'm going to put in a column for A times B naught. and a column for B naught times C. Then I'm going to have a column for that sum. And then finally, for the inverted sum. Okay, I'm going to put in some vertical lines just to try to keep things a little bit neater so that I don't go crazy with my columns. Okay, might as well throw this one in for good measure. So this right here would be the output for the original. As for the simplified, looks like I would need an A plus C, then an A plus C inverted. And then I could finally do the simplified expression, the final expression. Okay, so I will need these three columns just to set up the right side. So A plus C, then A plus C all inverted, then B plus A plus C all inverted. And now I'm all set. So if this were a test question, you would get a mark for every single one of these correct columns. Okay, so let's go ahead and fill in all the zeros and the ones. So B naught. Now we have to multiply A and B naught. So 0, 0, 0, 0, 1, 1, 0, 0. Now we have to multiply B naught and C. So these two columns, 0, 1, 0, 0, 0, 1, 0, 0. Okay, so that was B naught multiplied by C. Now I have to add those latter two columns, so adding here. So 0, 1, 0, 0, 1, 1, 0, 0. Like that. And then I have to invert that. 1, 0, 1, 1, 0, 0, 1, 1. Like that. So that's my final for the original, my final column for the original circuit. Okay, this guy. Now I'm going to be doing this one. So it's this expression right here. So I'm going to do my A plus C first. So adding here, 0, 1, 0, 1, 1, 1, 1, 1. Okay, so that's for the addition. Now I have to flip all of those. Like that. Lastly, this column should be added with B. Okay, so we take this column and add it with B. So here we go, adding. Looks like 1, 0, 1, 1, 0, 0, 1, 1. So that is the expression corresponding to this circuit and this simplified expression. Now look how cool, they match. What a relief after all that work. Okay, so one more happy face and we are done. So I know this was a long one, this video, so I apologize for that, but I wanted to make sure I did 3 really good examples with you Suggested problems for you to try are listed in Blackboard. Thanks a lot for watching. Have a good day.